So as I said in the introduction, we're going to build our way up to the full so-called real number system that we use today. In a way that's got kind of a natural progression to it. Right? So this building is going to start with what really is the most fundamental set of numbers. It's the so-called natural numbers. You can think of these as the numbers that literally occur in nature, the things that we can count on our fingers. They're the numbers 1, 2, 3, 4, 5, 6, and so on. And you see we have a special symbol for them, right? It's that little N. If you look closely, you'll see there's a little extra line on that diagonal piece. Right? That's something you're gonna see in the symbols for all of the number systems that we're going to talk about. Now, I hate to do this to you right at the very beginning, but the natural numbers are one of those things in mathematics where there isn't exactly one universally agreed on definition of what it is, right? I've listed it here starting at 1, and that's the way I usually think about it, but sometimes you will see the natural numbers listed out starting at 0. Okay, and that is also acceptable, right? So if you're looking at some other stuff online, or maybe your textbook says something a little different, don't be surprised. That's a perfectly acceptable way to define these. So when we talk about natural numbers, one way we think about doing things with them is we can think about taking a natural number and either breaking it down into smaller natural numbers or building it up into bigger natural numbers. And I've got some language here for describing that. And I know that this seems like a very fussy, mathy definition, but it's really not. And it's something that you've probably already seen before. It's this idea of a factor versus a multiple, right? And the idea is if I can take a natural number, say 12, and rewrite it as the product of two smaller natural numbers, those two smaller numbers are factors of the original one. For example, 12 is equal to 4 times 3. Right? This means that 4 and 3 are factors of 12. That's kind of the breaking down direction. And from the building up direction, I would say that 12 is a multiple of 4 and that it's a multiple of 3. Right? So to keep those two straight in your head, right, the way I kind of try to remember it is to get a multiple, you multiply. Right? So multiples are always bigger than the original number. For example, 12 is a multiple of 3. Right? It's also a multiple of 4. Factors, on the other hand, go in the other direction and are always smaller. Okay, so these factors and multiples, they're not necessarily unique. It's always something mathematicians want to worry about, right? Is something unique? Well, they're not, right? And you can see that here with 12, right? 12 is also 2 times 6. 12 is also 1 times 12, right? In this case, there's several different ways that we can factor this one number. Now, sometimes the factorization of a number is unique. Sometimes there is only way we can do it, and that one way would be 1 times the number itself. For example, 13. Right? I can write 13 as 13 times 1, and that's it. There are no other two natural numbers that I can multiply together to get 13. Numbers that have this property are special. This is the first sentence here. If the only factors of a number are 1 in itself, that number is what we call a prime number. A composite number, on the other hand, like going back to my previous example, like 12, right, is a number that isn't prime. So it's just kind of everything else. Okay, 12 is composite because I can write it as 2 times 6, 3 times 4, lots of possibilities other than just 1 times 12. Now, composite numbers are nice. I don't want to sound like I'm bad-mouthing them, okay? But the prime numbers are really, really useful, both from a theoretical perspective and from a practical perspective, as you'll see as we go deeper into even just this section. There are lots of really useful, practical, everyday arithmetic, helpful kind of things that we can do using these prime numbers. So how can we identify a prime number? I mean, I give you a number, right, like 132, and I say, well, is it prime or is it composite? Ultimately, there really isn't a super good answer to that. I mean, there are some things we can do, especially with smaller numbers, but uh, as important as they are and as thoroughly studied as they've been, the prime numbers, in a lot of ways, really are still something of an enigma. Even when it comes down to something as simple as making a list of them. Now, you can find lists online, but they only go up to a certain point, and there comes a point where we really can't say in any kind of formula way what the next prime number is. You just have to kind of go and do some very brute force searching, and we'll talk about that a little bit on the next slide. But some things you can do is look to see if there are numbers that go into this, like 132, right? For example, does 2 go into it? Does 5 go into it? And so on. And there's some rules you can use to check for these really pretty quickly. For example, if the last digit of a number is divisible by 2, then the number is divisible by 2. So here the last digit is 2. Yeah, 2 goes into 2 evenly, goes in once. So this number is divisible by 2. And that alone is enough to answer my question. This number is not prime. 132 is equal to, among other things, 2 times, if you do the division, is 2 times 66. And that's enough for me to say it's not prime, it has to be a composite. Okay, but let's look at some other rules, because these can come in really handy here. And these are something you can teach even to relatively young children. If the sum of the digits of a number is divisible by 3, then the number is. All right, so take a look at my number here again. 132. The digits are 1, 3, and 2. If you add those up, 1 plus 3 is 4, 4 plus 2 is 6. 6 is divisible by 3. Therefore, 132 is divisible by 3. Right? If you get your calculator out, if you have to, 43 times 3, I think, is what that comes out to. You look at the rule for 2, right? For 2, you look at the last digit. For 4, you look at the last 2 digits. So that would be 32. 32 is divisible by 4. Therefore, 132 is divisible by 4. The rule for 5, if the last digit is 0 or 5, then 5 goes into the number. That's not the case here. And so 5 does not go into 132. Now, you notice I skipped 6. Right? Why did I skip 6? Well, 6 is equal to 2 times 3. Right? So if you want to see if something is divisible by 6, see if it's divisible by 2. See if it's divisible by 3. If the answer to both those questions is yes, then okay, 6 goes into it. And that was the case here. Right? 2 and 3 both go into 132, so 6 goes into 132. Okay, you'll also notice that I skipped 7. There is a rule for 7. It's a bit of a hot mess. So much so that I usually tell students, look, if you need to know if something's divisible by 7, just try to divide it by 7 and see what happens. And that's usually easier than trying to get that rule out and make it work. If the last 3 digits are divisible by 8, then the number is divisible by 8. You know what? Look at the 2's. Right? 2. Think of that as 2 to the first. You look at the single last digit. 4 is 2 squared. You look at the last 2 digits. 8 is 2 to the third. You look at the last 3 digits, so on and so on, and so on. So does 132, or does 8 go into 132? Well, at this point, the rule isn't very helpful. We're just going to have to do the division, and if you give that a try, you'll see pretty quickly, no, it doesn't. We've got a rule for 9s that's very similar to the rule for 3s. You add up the digits and see if that sum is divisible by 9. And in this case, it's not. Right? Remember that sum was 6. 9 does not go into 6, so 9 does not go into 132. And I got one more here. If the last digit is 0, then it's divisible by 10. That's not the case here. Right? So what do we get? We got 2 going into it, 3 going into it, 4, 6, and whatever you get when you do those divisions. So how about this one? How about 97? Is 97 prime? Well, just for practice, I'd encourage you to go through all of our tests here, and to give 7 a try. Get your calculator out if you like, right? Just see what 97 divided by 7 is. If you do that, you'll see that none of these numbers on our list here go into 97. Okay, so now what? Now it really just turns into a brute force exercise. Try 11. 97 divided by 11. not an integer. It's 8 point something or other. Uh, no need to try 12. We've already ruled out 2 and 3, right? So we can rule out 12. Try 13. Don't bother with 14. We've already ruled out 2, right? And 2 is a factor of 14. You don't have to try 15. We've already ruled out 5 and 3. So you can make your life a little easier, right? Even when you have to do this brute force approach. But if you keep going, try number after number, working your way up. You'll see eventually that no numbers go into 97. No integers, excuse me, no natural numbers go into 97 evenly. So 97 is a prime number. Okay, so let me give you a little help here at least. Okay, where do you have to stop checking? Right? At what point can you say, okay, obviously if you go all the way up to 96, right, then okay, you've tried every possible natural number less than 97. But that's a lot, and we can do better. If you ask your calculator what the square root of 97 is, you're gonna get 9 point something 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 something, right? Nine and some decimal. 9 is the biggest number you have to test up to, right? Once you get up to 9, you know, even if this was a composite number, there will be no number that if you've tested every number below the square root, then you've also crossed off every possible number above the square root. So that kind of gives you an upper bound, right, on how far you have to go to come up with an answer. So in the next lecture, we're going to kind of continue this conversation of prime numbers by looking at exactly how far can we push this factorization thing, right? Yeah, okay, I can break 12 down into 4 times 3, but can I go further? Right, well, look at that. Think about the 4. 4 is 2 times 2, right? So instead of thinking of 12 as 4 times 3, I could think of it as 2 times 2 times 3. And if we really kind of push that to the point where we end up with all prime numbers being multiplied together, we get something called the prime factorization, which is going to turn out to be a pretty useful tool in doing some other things as well.